Good morning, everyone. Welcome back to CS 2100. I understand some students are distressed in finding out that there's a quiz on Thursday. Um, I'm sorry about that. However, from day one, we announced what days the quiz would be. It's listed on the modules if you look at them. It's listed in the syllabus. It's listed about everywhere I can think of. And I've been announcing it since last Tuesday to remind you about it. So please come to lecture, go to discussions. Everybody's been trying to do that. There is a review session later today at 5 o'clock. Let me go through that. We've got a reminder once again that there's a quiz on Thursday. Basically, the way this class is run, we finish material on either a Tuesday or Thursday in a specific chapter. The homework is due at midnight the next night. That's why you're supposed to do the homework gradually, right when you're learning each section, not wait till the last minute. It's due the next night at 11:59 p.m. And then basically 5 or 6 days later is when the quiz is. Usually what happens is if we finish the lecture on a Thursday, the next Tuesday, like today, we start new material and then there's a quiz the following Thursday. If the last lecture is on a Tuesday, then your homework is due Wednesday night. We have different lecture material on Thursday and the quiz is the next Tuesday. So it's usually basically 1 week from the date, the quiz is basically 1 week from the date of the last lecture on that material. That's been true and is consistent for the whole semester. Okay, so let me remind you, there's a quiz. There's one remaining quiz review session today at 5 o'clock, run by Nancy. Use her Zoom link and password for office hours. The quiz material is the content in sections 3.1 through 3.4. They are the sections that you were supposed to have read, watched the videos on, done the pre-lecture problem sets, and done the homework on. You will not be asked about anything that is not in those sections or previous sections. Looking forward beyond Thursday, Friday is a no instruction day for the whole university, so we don't have any instructions. My reminder, there are no instructions, no discussion sections, no office hours. Monday and Tuesday of next week is the mini break that I scheduled for you. Yeah, is the mini break I scheduled for you. Quiz 2, I'm sorry, let me finish. The mini break I scheduled for you, there are no office hours, no lecture on Tuesday, no pre-lecture quizzes, no reading assignment for Tuesday because there's no class then. So it gives you a chance to play catch up, I hope. There is already homework assigned on chapter 4, which we're starting in the lecture today. Someone asks about quiz 2 returning. Yeah, I still have one thing I have to do this afternoon, and then the quizzes will be returned to you. They'll be published and put onto Canvas. I'm sorry for the delay, but it's a problem that we're trying to clear up. Okay. There's one thing that's not on the announcements. I'm informed that starting shortly, anytime that we're recording, or I assume that applies to live streaming, because that records it as well. You are supposed to give your consent knowing that this class is doing that. I think the provisions we give you are more than the university required. So I'm not sure whether you will have to agree to this when you log in or when I turn on the streaming or what, or maybe you won't, I'm not sure. But let me remind you what the class allowances are for that. So the first allowance is that I would appreciate if you did keep your cameras on and your name's visible, so I'm not talking to blank screens. It makes it easier. I appreciate those of you who do. If you feel uncomfortable having your face recorded, you can turn your camera off. That is an option the university also now is allowing. We've allowed it from the beginning of the semester. If you feel uncomfortable with your name being projected, then if you send me a message, instructors a message in Piazza or in Canvas, we can agree upon an alias for you that you can use, and that way the instructors will know who you are, but your name will not appear. If it bothers you to have both your name and your image up, you can use both of those options. The university says if it bothers you, you can turn it off and go watch the recording later. We've got the third option that you can turn off your camera and use an alias, an approved alias, and participate in the class, which I like because then you can ask questions when you don't understand something. And of course, we are streaming so that you can come back and look at, so that you can come back and watch the quiz. I'm sorry, watch the lecture as before. Are there any questions about that? I don't know when that starts. I know it's supposed to start maybe next week or something. I don't know. But are there any questions about that? Anyone feel uncomfortable with the provisions that we already have in this class? Okay. Good. Let's go on. So let's do a practice problem. Okay. So for Boolean algebra, we're supposed to prove, this is a review, if A plus B equals B, then AB equals A, using the Boolean algebra version of Theorem 6. Okay, so I don't have the Theorem 6 in front of me. So why don't you all give it a try and then we'll go through it in class. You could be asked something like this on the quiz. Okay, so instead of scribbling this answer, I'm going to use the typed one so everybody sees it and sees what would be expected of you on the quiz to identify and do a complete problem. Okay, Of course, you won't be able to, well, you could type it, but most of you won't be typing it. So you would write this by hand. Okay, so what do you have there? So we rewrite what you know, that B is equal to A plus B. And then we multiply both sides by A. If two sides are equal, then multiplying them by the same thing doesn't change the equality. So that gives us that AB is equal to AA plus AB. But AA is just equal to A. And why is that? That's the idempotent rule. Yes, you son.
Hi, I just want to ask that why can't we move B to?
I'm
Why
sorry,
can
I
we?
can't understand what you're saying.
Oh, hello. Can you hear me?
Yeah, I can hear you. Try again.
Okay. I just want to ask, why can't we move B to the other side and make A equal to 0?
Because we don't know that A is equal to 0.
Oh, I'm saying. So it says if A plus B equal to B, if we
Yes.
move B to the other side, then we want to be
The minute
B minus
the minute you assign a value, you're not making any kind of allowance.
Wait, I can just send
What
it to you.
does that mean?
What does that mean? It's not general. If you assign a value, it's like saying let A equal 3 and then saying, well, it works for A equal 3, so it must be true for everything. That's not acceptable. That's not a proof. We have to start out and not know anything about it. Other than that, it's a Boolean variable.
Okay, to be honest, I thought it was
So you're saying there cannot contain any number in the proof. That's all.
No, just the variables. You can't assign a number value.
All right, cool. Thanks.
You put your hand down. So here we go. So AA is equal to A because it's idempotent. Then we can say that, well, there's another rule that applies right here, but for the moment, let's take this. So then we can say, well, that's just A times 1 plus B. That is the distributive law. And then 1 plus B, what's that equal to? Well, that's always equal to 1, no matter what B is. Why is that? That's the universal bound. And then A times 1 is equal to A. That's because of the identity. Okay, notice that we're just using these short one-word statements. And then we've shown that AB is equal to A, and we're done with the proof. Are there any questions about how long it took? Okay.
Excuse me.
Yes.
Maybe we should label one more step to make this more clear, because after I don't pretend I think we should write A is equal to A times 1 plus A times B, then we can get a distributive.
I'm sorry. Oh, why does this apply?
Yeah, I just think we should add one more step to make the process more clear.
Yes, okay, we can do that. We can put one more step in here and say, well, that's equal to A times 1 plus AB. And that's, why is that? That's the identity.
Yeah, now makes sense. Thank you.
Very good. Okay. So that one gets squeaked in there. Grant.
Yeah, there's a good question in the chat, and I was just wondering, Jordan asked it, if you could go over it.
Can you plug in A plus B for B in A equals AB? This statement here is what you're trying to prove. You don't know that to start with. You could say AB is then equal to A times A plus B, which is equal to AA plus AB, which is equal to, I'm leaving out the steps, which is equal to A plus AB. And what is that equal to? That's equal to A. Okay, I'm going to have to look up which statement it is, which is why I provide those to you. So someone asked, would we provide chapter theorem 6 in chapter 3? And the answer is yes. I will provide theorem 6 in chapter 3. I will not provide the Boolean version of it. That means you have to be able to transform, what do we have here? Well, it's here somewhere. We'd have to prove it. So we'd have to go backwards and get there. Okay, what would the set version of, what is, if I transform this to sets, what does that turn into in terms of sets? Anyone want to take a stab?
Absorption.
Let me remember here. Yep, it is. But what does it turn into here? It turns into A union, the intersection of A intersect B. So if you're not sure, you can always change it around like this. And that is indeed absorption. Good, you found it faster than me. So both of these ways work without any problem at all. So there is not one proof, there are many. Christopher.
Sorry if you've answered this already, but do you know if theorem 6 will be provided for us?
I thought I just said that, yes.
Oh,
it
sorry,
will.
I must have missed it.
That's okay. That's okay. Keep your sound on. Theorem 6 will be provided for you. The corresponding version of it for Boolean algebra will not be provided. So you have to be able to turn it like that these are the equivalent statements. Okay, I'm just going to provide one of them, not both. It takes me forever to type it in and turn it into LaTeX. So once was enough. Okay. All right. All right, let's do another practice problem to review it. This is a longer one. Let A equal to 2 times K, the set of all integers of the form 2 times K, where K is an integer. Let B equal to the set of all integers 4 times K plus 1. And let C equal to the set of all integers of the form 4K plus 3. Prove that the set of sets T equal to ABC is a partition of the integers. Do you want to give that a start and try? Remember, we have to prove 3 things to show that something is a partition. So if you don't remember what they are, put that on your index card. Okay. I'm cutting it short so we get done with everything today. What are the three things we have to use? By definition, what are the three things we have to show? So T is a partition. If and only if, 1, A is not empty, B is not empty, and C is not empty. Property 2, that A intersect B is empty, A intersect C is empty, and B intersect C is empty. I'm rewording the general statement to this particular group of sets. 3 is that A union B union C is equal to all integers. That's a Z. Okay, those are the three things that we have to show in order to guarantee that this is a partition. So the first one, how do we show that?
We find a value in each set.
Yep, that's exactly right. So what do we have here? We have 0 equal to 2 times 0 is in A, since 0 is an integer, which you'd have to write down. 4 is equal to, nope. 1 is equal to 4 times 0 plus 1 is an integer in B, since 0 is in the integers. And finally, 3 is equal to 4 times 0 plus 3 is in C. So they're not empty. Okay. So it doesn't have to be terribly long. You just have to show, but you would have to say, since 0 is an integer, we've shown the form that they take on. Okay. 2, we have to prove that their intersections are disjoint. So that's 3 little separate proofs. So we have to say, suppose X is in A intersect B. Okay, we're doing this by contradiction. Suppose the intersection is not empty. Then X is equal to 2K for some K and equal to 4M plus 1. 4M plus 1 for some K and M in Z. Okay, that's the definition of each set. Okay, so that would say that X is equal to 2K, and also X is equal to 2 times C plus 1, where C equal to 2M in Z. And that says, that implies that X is even and X is odd. a contradiction. That's impossible. So A intersect B equals the empty set. Okay? Now to complete this proof, for step 2, do we have to prove the contradiction that there are no elements in all 3 possible intersections? Yes, that's exactly what you have to prove. And you have to do that for all possible sets of 2 intersections of elements of the partition. Okay, what's step 3? You have to prove that A union B union C is equal to the integers. Okay, so we know A union B union C is a subset of the integers because each one is a subset, so the union is. They're defined as elements. So now we have to show that Z, the integers, is a subset of A union B union C. So how do we do that? We do that with an element-wise proof. So let P be in Z. Then, by the division theorem, I told you we'd need this here too. Theorem. P is equal to 4Q plus R. That's an R. Where R is greater than or equal to 0 and less than 4. Okay, case 1. For R equal, I can't remember the sets, but let's try 1. R equal to 1, then P equal to 4Q plus 1, which is definitely set B, right? Grant, yes.
How do we know that A union B union C is a subset of C?
Is A a subset of the integers by definition?
Okay, so we're just getting it from each of the definitions then.
Exactly.
Okay.
If 3 sets are subsets of the integers, then their union has to be a subset of the integers.
All right, makes sense. Thanks.
So someone asked, where do we get P equal 4Q plus R? We get it from the division theorem in chapter 2. You still have to remember that. You can't forget that again. Okay. So then P equals 4Q plus 1, which is the definition of B. So let's say case 2, we're saving 2 cases, is R equal to 3. I think that's what we need here. Yeah, 3. Then P equal to 4Q plus 3. And that's by definition an element of C. So now we do the other 2 cases. Case 3, R equal to 0. Then P is equal to 4Q, which is equal to 2 times 2Q, and that's the associative rule there. That's equal to 2 times C for some C in the integers by closure. And by definition, that's in A. Okay. Finally, case 4, R equal to 2. Then P equal 4Q plus 2, which is equal to 2 times 2Q plus 1, and that's distributive property. And that's equal to 2 times C, where C equals to 2Q plus 1, is an integer by closure under mult and addition by closure of integers. Okay. So what does that say? Well, that says 2 times C. Well, that's an A. Thus, Z is equal to A union B union C. Okay, then you would end up with one more sentence that says, thus we've proved that all 3 defining properties of a partition hold, and this is a partition. Okay? Okay, good. One more practice problem. Use an element-wise proof to show that if x is less than -3, well, the set of all x less than -3, the set of all integers less than -3, union the set of all integers greater than 3 is contained in the set of integers whose square is larger than 9. Okay.
And is it real numbers, not integers?
Oh, yep, real numbers. You're right. When I use Z, my brain goes off. Yes, real numbers, absolutely. Thank you. Okay, should we start or give you a chance to go through? Let's give it a whirl. So if x is less than -3, then x minus 3 is even more less than negative than 0, okay? So if x is less than -3, then x minus, that's less than -3 and less than 0. And also x plus 3 is still less than 0. Okay, so when I multiply 2 negative numbers, what's the product of 2 negative numbers? Well, it's positive, right? So if 2 negative numbers are less than 0, then their product is positive, and that's equal to x squared minus 9. So since that's positive, then 9 is less than x squared, and x is in, let's call this set C. X is in C. So now we go the other direction. We say, suppose x is greater than 3. That says, suppose it's in the second set. Do we have to do both of them? Yes, because it could be in these 2 sets are disjoint. So it has to be in one or the other. And you must show it for both. Remember, that's a union, not an intersection. Okay, so now x is bigger than 3. So x minus 3 is still greater than 0. And x plus 3 is even bigger, greater than 0. So then 0 is less than x minus 3. times x plus 3, it should look familiar, which is x squared minus 9. So 9 is less than x squared, and x is in C. So in both cases, we've shown that if there's an element in this set or an element in this set, it's contained in the right set. Isaac, yes.
This may or may not be a good question, but so I'm wondering which property you use to show that 0 is less than x minus 3 times x plus 3. Is it just obvious?
That the product of two negative numbers.
Okay. Okay, yeah, that makes sense.
You can change them into absolute values and go through that, but the product of two negative numbers is positive. Okay? All right.
Yep, thanks.
Let's start with the new stuff. In fact, let's have a break and then do the new stuff. So it's your 5-minute break right now. We're on time for a change. You can ask me any questions you want right now during the break.
In the most recent example, how did you go from x minus 3 is less than negative 3 is less than 0 to x plus 3 is less than 0? Did you just add? Yeah, I'm confused.
I added 3 to both sides of this inequality here. So if you add 3, if you have an inequality and add the same number to both sides, the inequality holds. It's not multiplication, it's addition. Multiplication flips a sign, flips an inequality, but addition keeps it the same. So if I have x minus 3, x plus 3 on this here, and then I add 3 to minus 3, I get 0. So I get x plus 3 is less than 0. Okay?
All right, thanks.
You can sort of ask, well, how do you know to do that? And for that, you have to look at what that clue is telling you.
I have a question on the practice problem number 2.
Yes, ma'am.
When we're trying to prove that the union of A, B, and C is equal to Z,
Yes.
don't you have to prove, like with 2 cases, that A union B union C is a subset of Z and Z is a subset of A union B union C?
By definition, A is a subset of Z. I'm just going to write it like that because I never write it clearly. And B is a subset of Z, and C is a subset of Z. So if I have 3 subsets of a set, then their union has to be a subset. You don't have to prove that.
Cool, thanks.
This is by definition. If you didn't know that they were each subsets, then you would have to prove it. But you do know it. Okay?
Sorry, one more question on the problem 3.
Yep.
Would those be considered 2 separate cases, or is that just kind of does it matter?
You can call it case 1 and case 2, or part 1 and part 2. Whenever you have something of the form A union B is a subset of C, that you have to show that, if you have to show that, then the X, usually we say let X be in A union B. Then by definition of union, that means then X is in A or X is in B. Now, when we write or there, X could be in the intersection, but you're covering it by saying it's in either one and showing it for that case. Okay, so since you have 2 possibilities, you must show it for both of them, whether you call them cases or parts or sub things is up to you.
Okay, and then last question, but since it's y, or the variable is y in the second set, does it matter that you used x? Or
No, we're using the variables that are used in defining a set are dummy variables.
okay, so I
Okay.
say x is an element of y is greater than 3, such that y is in all
Yeah,
fields.
that means that X is that if it's in there, then you know it's bigger than 3, period.
Okay, thanks.
Okay, it's because when you're defining it like this, it's dummy variables. You know what I mean when I say dummy variables?
Yeah, I mean, specifically, I was just wondering in the statement, let x be whatever. I was just wondering if like we could have two variables that didn't match up. So let x be in the set.
I could have said A. I could have said Q. Basically, what we're doing is saying, suppose, well, we're saying this. So then we say, let X be in A. And then we say, well, what does that mean? That means X is less than -3. I
Okay,
did leave out some steps, but
no, that makes sense. Thanks.
okay. Okay, it's time. Let's talk about functions. So if we're given two sets, A and B, they can be infinite, finite, discrete, or not. It doesn't matter. A function from A to B relates each input element of A to an element of B. And we write that F takes A into B. Each element of A, that means every element of A has exactly one output. Every single one has an output. The set of all inputs is called the domain. The set of outputs is called the codomain. Now, the outputs don't have to be the whole codomain. The collection, the set of all outputs is called the image or the range of F. Okay, and the rule defining how the inputs and outputs are related is designated by a letter frequently, or a list, or some other way, or an arrow diagram. There are many ways to describe the rule. So you can use arrow diagrams, and we're going to have some examples. You can use algebraic expressions that tell specifically what element in the codomain is associated to a specific element in the domain. Okay, so if I write the domain is R and the codomain is R, I can say f of x, given x a real number, its image, its output will be x times x, or x squared. Okay, sometimes you use set notation. You can use two different kinds of set notation. You can say the set of all x, y in R cross R, such that y is equal to x times x. Or you could say the set of all x, comma, all pairs x, comma, x times x, where x is in R. Both of them describe, all three describe exactly the same function. And depending upon what you need it for, any one of them may be a better description. They're all equivalent, but given a problem, that may be what you like to do. Notice that in our examples here, the image of the functions are the non-negative reals. The codomain is all the reals. Okay, so the image and the codomain are not the same. Okay, the codomain is the one you're selecting outputs from to create the image. Okay, here's an example. For a set ABC, define the function C that goes from the power set of X to the power set of X with the rule that the image of the input A is a subset of the power of X. So it's an element of the power set. It's equal to X, the original set, minus A. So let's look at what the power set is here. We're supposed to make a two-set diagram, so that's the right thing anyway. So what do we have here? We have the power set is equal to the empty set. It's equal to all of the one element subsets, all two element subsets, and X. You can just write an X there if you like. So that's the domain here. The codomain is here, and we just rewrite the same thing. Okay? So what is C of the empty set? Well, it's equal to X minus the empty set. What is X minus the empty set?
X.
X. Someone asked, why is the codomain equal to the domain? Because in this case, we defined the function going from the power set of X to the power set of X. So this is the domain, and this is the codomain. Okay? Good. So let's see. This goes all the way down to here. Okay, what is C of set A?
Would it be BC?
Yes, it'll be BC. Exactly right. What is C of B?
AC.
AC, very good. What is C of the one element set C?
AB.
What is it?
AB.
It would be the set AB.
Yes, set AB.
So that would be this one. Okay, what is C of AB?
Set C.
Yeah, it's the set consisting of the one element C. Now notice something here. I'm not going to do that, but we end up seeing that so the way that this is done, since we're looking at the complement in X, if BC is the complement of A in X, then A is the set, the one element set A is the complement of the set BC in X. So this one and this one, we notice that A goes to BC, BC goes to A. Okay? Hold on to that. We're going to use it again. Does everybody understand this picture? Good. There's a better one. Okay, a relation or binary relation consists of three components: a domain A, a codomain B, and a rule that generates a subset of the Cartesian product A cross B. Notice it is ordered. Okay, so you have ordered pairs that define a relation. It does not have all the elements of A. So all the elements of A may or may not appear as the first element of something in the relation. Okay. Furthermore, you can have one element in the domain paired with many elements in the codomain. So a relation may not be a function at all. Okay. Some relations are functions, but not all. I like this example. Let A be the domain, the set of residents of Salt Lake City. B be all the kinds of flowers that grow in the Salt Lake City climate. The rule A that pairs A and B is the resident A has flower B growing in their garden. Now, there may be some residents of Salt Lake City that live in condos and don't have gardens, so they're not in here at all. There may be residents of Salt Lake City that have lots of flowers growing in their garden. So they would have more pairings in that case. Okay, so what would this look like? Well, if we just moderated down to a few, we could have 6 people living in an apartment building, and they have access to a community garden. And they can grow 6 types of flowers. They can grow roses, tulips, daffodils, irises, chrysanthemums, and geraniums. They're the only approved ones for this example. Okay, so what kinds of relations can we make? Well, there are lots of them, but let's pick a few. Our first example says all 6 people want to grow flowers and they all like roses. So all 6 people are growing roses. Is that a valid relation? And does it have any special characteristics? It is a valid relation. It has the characteristics that each person, each element of the domain maps to exactly one element. First of all, that each element on the domain is in the relation. And second of all, it maps to one specific value. The fact that they all map to roses is fine. Okay, the codomain can have many elements of the domain mapping to it. Okay, let's pick another one. In this one, person 2 and person 5 don't have any interest in the community garden. They don't want to grow anything. They're not in the relation at all. But person 1, well, that person likes daffodils and tulips. And so we have 2 arrows going from person 1 into the flowers. Person 3 likes irises. You don't want anything else. Person 4 likes geraniums and only geraniums. Person 5, well, they're not in it. And person 6, well, person 6 likes irises and chrysanthemums, one for the spring, one for the fall. So that person has 2 types of flowers emanating from him, her, they, them. That's a valid relation. Is that relation a function? Someone says no. Good. Why not?
Because person 1 maps to 2 different flowers.
That's one reason, yes. Is there any other reason?
Not every element.
That would be enough, by the way, if you were asked to state why, but there is another reason that you could use it instead. What would that be?
Not every element in the domain is mapped to an element in the codomain.
Perfect. Very good. Very good. Yes. So it's a valid relation. It's not a function. Here we have another example. what do we have? We have everybody likes some kind of flower and everybody likes a completely different one and only one. Each one is growing only one type of flower in their garden plot. Is this a valid relation? Someone says yes. Tell me why. Okay, come on, guys. It's a valid relation simply because there are arrows. A relation just is a collection of pairs, so that's okay. Is it a function? Someone says yes. Why is it a function?
Because the inputs always have an output and there are no multiple outputs for one input.
Perfect. That's both reasons. And you need both of them to apply for it to be a function. That's not an or, that's an and requirement. Very good. Keep that picture in mind. We're going to use it again later. So as we see, functions are special cases of relations. All elements of the domain are used and paired with exactly one element of the codomain. You can write a function as a relation, and then we use a capital letter F and write it as a subset of domain cross codomain. Graphs in chapter 7 that we'll cover are relations on the set of vertices. They're considered to be the elements. And it's an arrow diagram. Are all relations also functions? No, we just had our examples. Speak why not? Because an element in the domain may not be used in the relation. An element in the domain may be in the relation with more than one element in the codomain. So you all got that right. Very good. Okay. Let's do an example here. Suppose R is a relation on the set n cross n. What is n?
Natural numbers?
Sorry?
Natural numbers, I believe.
Yes, natural numbers. What are the natural numbers?
Non-negative integers, I guess. Is this?
Yes, excellent. That's perfect. The non-negative integers defined by the relation that x and y are related if x squared plus y squared equals 25. Write R is a set of ordered pairs. So here's R. Here's R. Let's see. Let's start with the natural numbers. Can I make 0 an element in the pair? What does that go with? 0 squared is 0. Is there a y such that y squared equals 25?
5.
Yeah. 0, 5. That's an element. What about 5, 0? Is that an element? Yeah, and they're not the same. Ordered pairs, the order matters. Okay, what else do we have? Can I use 1? Well, let's see. Is there an integer squared equal to 24? No. Nope, can't use 1. What about 2? 2 squared is 4. Is there a number squared, an integer squared equal to 21? What I'm doing is saying, picking x and seeing if I can find a y. Okay, so if I pick 2, then 2 squared is 4 and 25 minus 4 is 21. So I don't see any way to use 2. What about 3? if I x is 3, and then 3 squared is 9, 25 minus 9 is 16. Is 16 a square?
Yes.
Yes. So I have 3. And what is 16 the square of?
4.
Good. Well, that must mean I can also have the pair 4, 3. Is there anything else in the relation?
Maybe that's all.
Maybe that's all. Maybe definitely that's all. Okay, so look what we have here. We start with a set. The natural numbers are infinite. So we have infinite cross infinite, and we end up with a relation that has just 4 elements in it. Okay, it's definitely not a function on the natural numbers, because then I'd have to have an infinite number. Okay. You're right. Good. Okay, let's move along. So one set arrow diagram. When the domain and the codomain are the same, the arrow diagrams for both relations and functions can be written with just one set. So let's have a look at an example. Here's one. We're going to do both diagrams, a 2 set and a 1 set for this one. So we have both domain and codomain are the set X, which consists of the integers 1, 2, 3, 4. So let's do our 2 set diagram first. Here we have 1, 2, 3, 4, and that's the domain. And here we have codomain. 1, 2, 3, 4. Okay, what are the pairs? Well, we have 1 goes to 1, so we have an arrow going from 1 to 1. 2 goes to 2, so we have an arrow going from 2 to 2. 2 goes to 3, we have an arrow going from 2 to 3. 3 goes to 2, we have an arrow going from 3 to 2. And 4 goes to 2. 4 goes to 2. Notice everything in the domain is mapped to something in the codomain. It's not a function because 2, the number 2 goes to 2 different things. Okay, so let's make a 1 set diagram here. 1, 2, 3, 4. So how do we write that? Well, let's see. 1 goes to 1. So I have an arrow from 1 to 1. Emanates at 1, it ends at 1. 2 goes to 2. So I have an arrow going from 2 to 2. 2 goes to 3. So we have an arrow going from 2 to 3. 3 goes to 2. Okay, we have another arrow going that way. And 4 goes to 2. We have an arrow from 4 to 2. That's the same. This is a 2 set of that relation. And this is a 1 set of that relation. Okay. A 1 set diagram is also called a graph, as I said. Okay. Any questions? Good. Inverse relations. Given a relation R with domain A and codomain B. So we're back to 2 arbitrary sets for domain and codomain. The relation R inverse with domain B and codomain A is called the inverse of R and is defined so that BA, the pair, BA is in R inverse if and only if AB is in R. Okay? So here's a picture. We've already got that. So what is R? What are the set of elements in R? Well, we have person 1, and that goes to, I'm just going to write a T for tulips, okay? That's not true, that's tulips. T for tulips. And 1 for daffodils. 1 likes daffodils. 2 doesn't go in there anywhere. 3 likes irises. Okay. 4, what does 4 like? 4 likes geraniums. G for geraniums. 5 doesn't appear. 6 likes irises. And 6 likes chrysanthemums. And that's it. So what is the relation? Sorry about that. What is the relation R inverse? Well, what we do is we look at the first one in R, and R has 1 going to T, so R inverse has T going to 1. Remember, R inverse is defined on B cross A. R has 1 going to D, so R inverse has D going to 1. R has 3 going to irises, so R inverse has irises going to person 3. R has person 4 liking geraniums, so we have geraniums going to person 4. Person 6 is paired with irises, so irises get paired with person 6. And what was C? Chrysanthemums. Person 6 like chrysanthemums, so chrysanthemums like person 6. And that is R inverse. Can anyone guess what the arrow diagram for R inverse would be?
It would just be the same arrows with the direction flipped.
Exactly right. The directions of the arrows would be reversed. Inverse just reverses the directions of the arrows. Okay. Good enough. Okay. Oh, we already did that one. Good enough. Practice problem 7. Let R be the relation on A defined as set A is 2, 3, 4. Define less than so that X less than Y, meaning X is less than Y. So write R as a set of ordered pairs. What do we have here? We have R equal to, let's see, is 2 less than 2? No, that's not there. Is 2 less than 3? Yep. 2, 3 is there. Is 2 less than 4? Yep. 2, 4 is there. Is 3 less than 2? Nope. Is 3 less than 3? Nope. Is 3 less than 4? Yep. That's R. Okay. What is R inverse? You tell me now.
3, 2,
Yep.
4, 2, and 4, 3.
Yep. Okay, very good. Okay? Good. Inverse functions. So if we have a function a, f that goes from a to b, and a function b that g that goes from b to a, they're called inverses of each other when f of a equals a particular b, if enough, only if g of that b equals a. And that's true for all a and b and b. So that means that both f and g have to be functions. That's called inverse function. Function. So they both have to be functions. Okay. So what kinds of functions have inverses? Well, domain and codomains matter for the same rule. Sometimes you could have inverses if you have specific domains and codomains, or sometimes they won't exist if you have the wrong domain and codomain. So here's an example. If a and b are both the integers, and you let f of a be 2 times a for all a and a, can it have an inverse? So what is the image or range of f? We can write that as saying, what is f of a here? Well, it's equal to all even integers. Okay, so here's another question. So even integers are a subset of the integers. So I would need a function g that was defined on all of the integers, going from integer to integers, such that, suppose I have, here's a in the integers, and then f of a is 2 times a. Okay. Now that means that's how we define a. So what I would need is something that would take an integer b and pair it with something in the integers so that it worked. So if I call this b, then it's okay because I have the even integers. But suppose I take an odd integer, suppose I take 1. Can I map 1 to something? So, and the answer is no, I can't. Okay? Because, yes, Isaac.
Just a quick question. So this isn't true because we've defined the domain as z. Could we define the codomain as even numbers?
Yes, we can.
Okay.
Then do we have an inverse?
I believe so.
Yes, you're right. So this is where the domain and codomain really matter. Here's another example. Let a be all the real numbers. Isaac, if you're done, could you put your hand down? And b be the positive real numbers. And let f of a be defined as a squared. Can that have an inverse? Well, I can make the function g of b equal to the square root of b. And by definition, when we write that, it always means the positive square root. Okay, so if I say, well, suppose that's the inverse, then if a is greater than 0, then I square it and I take its square root and I get right back to a. But if a is negative and I square it, then g of a positive number is going to be positive. I can never get back to the negative values in z. I never map back to them. So here's a case where the domain matters. We just can't do both of them. So in the first case, it was the codomain that was too big. In the second case, the second case, it's the domain that's wrong. Okay. Here's a practice problem 8. Okay, here's our function C from before on the power sets. And I asked, does C have an inverse?
I would say yes.
That's the one set diagram for it. Who would say yes? Who is it?
Isaac.
Hi, Isaac, you're right. Tell me why. And what is it?
Because, well, the way I've been sort of looking at it is that both the domain and codomain have a perfect mapping, which means one maps to the other 1 for 1. Which means when you inverse, it always goes back to a place. And so there's always, when mapping, there's always a place for it to go and a place for it to go back to.
You're right. Okay. We can look at it here. What is the inverse of the function C?
The function.
Here, C is a function. What is its inverse? Its inverse is itself. Here, if I take 0, it goes to x. And if I apply it again, that goes to 0. It goes back to the identity. If I take AB, it goes to the set C. If I look at the set C, it goes back to AB. So in this case, C inverse is equal to C itself. Okay, let's get to this something that's a little bit better. Relations have inverses that are relations. Functions may or may not have inverses. When considered as a relation, the relation always has an inverse. Okay, what does that say? That says, oh, I won't get there on this one. We'll have to get to that next time. Let's talk about composition real quick. If R1 is a relation with domain A and codomain B, and R2 is a relation with domain B and codomain C, then the relation R3 is defined as the composition of R2 with R1, written R3 is equal to Z of all A and C if and only if there exists a B and B such that AB is in R1 and BC is in R2. Okay, so that defines it for us. It's called the composition of R2 with R1. So here's an example right here. Okay. What would the composition map be here? Well, let's see. R1 doesn't map to anything. It's not there. So let's see. 2 maps to 1, but then there's nothing that maps it to 3. 2 maps to A, B, C, D, and D maps to R. So we would have 2 maps to R. That's a 2 maps to R. But 2 maps to E and E maps to P. So we have 2P. And then we have 3 maps to E and E maps to E. So we'd have 3P. And that would be R3, which is equal to R2, 2 composed with R1. Okay. Function composition. Function composition says if you have a function from A to B and another function from B to C, we can define a composite mapping or composition written as H equal to G of f of x, and it's called the composition. So we can write it like this or like that, both ways. The function that's the composition H is on the domain of F, and it has codomain of G. Okay. So here's a simple example. So if I have F from integers to integers by F of M is equal to 2 times M plus 3, and G of N equal to N squared, then G of F of P is equal, of M is equal to 2M plus 3 squared. We do the F first, and then we square it. Okay, since both functions have domain and codomain equal to Z, we can also say, what is F of G of Q? Well, in that case, we apply G first, so we square Q, and then we insert it into F and add 3. So notice that composition is not commutative. Okay, and with that, I will stop and we will resume practice problems and new stuff next week. Thursday is the quiz. Okay, if you are having trouble submitting, you must indicate it before the end of the submission time, and you must have a note. If you're having internet trouble, you have to tell us why. And you have to provide something like something from Comcast saying you have an outage or something like that. Okay, if you want, you've got to try and make sure in advance that your internet is stable and your router's working and everything is okay. If you're in a glitchy situation, try and go to one that isn't glitchy. And with that, I'll say after if anyone has questions, but meanwhile, I think it's time that we have to stop.
Thank you.
So,
Thank you.
are there any questions?
Thanks.
Thank you all for coming. Good luck on Thursday.
Thank you.